Hello, how would you be able to calculate the electric field at some distance from a charged wire like this? In this video, I'm going to show you how to do that using Gauss's law. So here's the situation. We've got some wire and it's charged with positive charge. It's got a net positive charge of Q. We want to know the electric field somewhere, some distance, let's say R from the wire. How are we going to do that? We're going to use Gauss's law. So let's take a look at this in a little bit more detail. What do the field lines look like coming out of this positively charged wire? Now notice the charge isn't moving, so it's not carrying current. It's just sort of like a rod that's sitting there and it's got a whole bunch of charge on it, okay? Later on in the course, we'll talk about what happens when charge is moving that'll produce currents. But for right now, the charge is static. And so the field lines coming off of it are always going to be perpendicular to this thing. It's perhaps easiest to start here with the end view of the wire. So this from the top, let's say, just looks like a point charge that we've dealt with before. So here's our little charge, and every time I put a positive test charge near it, it's going to run away from it like that. That's what defines the field lines. Now, if I have a wire like this, then you're going to have these field lines coming off at different heights like that. And so they're going to be like spokes coming from a bicycle wheel, but many bicycle wheels stacked on top of each other like that. So that's the side view, and this is the end view right there. Now, remember, in Gauss's law, what we want to do is pay attention to how these field lines come away from the charged object. And we want to enclose this object with a Gaussian surface such that all of the field lines penetrate the surface in a perpendicular fashion. So, I would claim that the best surface for this is a cylinder. So let's start with the top view here, or the end view of the wire. It's just like we dealt with before in a previous video where we had a point charge and we enclosed it with a sphere, okay? But here what we have is a charge, and we're looking at the top end, as if we're at the top of this thing looking down, and we put the Gaussian surface around it like that, such that all these field lines are going to make 90-degree angles at all these points right there. It's 90 degrees with the surface in green. Okay, so far so good. But because we have so many of these stacked on top of each other, what we need to do is take this circle shape and basically drag it through space. When we do that, we get a cylinder like that. So the cylinder is kind of wrapped around the little axle right in there. I mean, in a way, it's a little bit like a jelly roll if you've ever eaten one of those. It's got jelly in the middle. That would be kind of like this. And then it's got some dough that's wrapped around it like that. So it's in a roll like that. Okay. So this is what it looks like. Now, how do I calculate the area of that Gaussian surface? So here's where it involves a little bit of three-dimensional imaging, okay? Imagine we take this sort of circle like that is a cylinder, okay? And now here's a perspective view of it here. So I'm just looking at this right there. So it's a little bit like I have a sheet of paper that I've rolled up around a pencil. Okay, so I've got a pencil and I've rolled a sheet of paper around it like that. And now what I'm going to do is I'm going to cut it along this dashed line. And as I do that, the sheet begins to unfold a little bit. And then I can flatten it. And if I flatten it, I get something like this. And I want to calculate the area of this because we'll need that for Gauss's law. As I said in previous videos, it's going to be the electric field times the area of the Gaussian surface that equals Q enclosed divided by epsilon naught. So what we're after right here is getting the area of this Gaussian surface that we picked. This Gaussian surface indeed intersects all the field lines in a 90-degree manner. So it's exactly what we're looking for. It's E-perpendicular. But the harder part is just calculating the area. Well, there's two things involved. One is going to be this distance here, which is the length of the cylinder, which is this distance here, which is this distance here, which is this distance here, or this distance here. So that's going to be L. We'll call it the length of the cylinder. That right there is this dimension here, okay? The other dimension is this, the distance around the circle. That's this. That's also this or this. And if we're a distance r away from the axle, if you will, if that's our distance r, then the circumference of a circle that has a radius r is just 2 pi r. So the basic, dimensions of this thing is 2 pi r times L. That's going to be our total area. So that allows us to calculate the surface area of the Gaussian surface that we put around this charged wire. So let's go to Gauss's law. Gauss's law is E perpendicular times A equals Q enclosed divided by epsilon naught. And remember, what we're trying to do is solve for the electric field. And this is E perpendicular, represented by the perpendicular sign there. That means that all of the field lines are penetrating the surface in a 90-degree manner, which we set up with this cylinder that we talked about in the previous slide. So, okay, what we're going to do is we're going to divide both sides by A, and we're going to isolate E perp on the left-hand side, and then solve for that. Then we'll get a formula for calculating the electric field at any distance r from that charged wire. So, we said that the surface area of that Gaussian cylinder, we picked a cylinder, was 2 pi r times L. So here's what we have, E times 2 pi r L equals Q enclosed, the total amount of charge that's inside that wire, or that is on the wire that is enclosed by our Gaussian surface, divided by epsilon naught. Now we just have to solve for E. And because all the field lines are indeed perpendicular, we can just call that E in the next frame. Okay. So I divide both sides by 2 pi RL, and I get this formula here in the box. That's the formula for the electric field at some distance r from the charged line. And what you'll see here is that it does depend on r. The further away you go, the smaller and smaller E will be. Now, some people like to point out that Q enclosed divided by L is sort of a charge per length value. And sometimes in some books, what you might see is that people basically represent Q divided by L by a parameter, they'll call it lambda, which is just charge per length. I'm not going to get into that in this course here. I just hope you understand the basic idea that it is some amount of charge over some amount of length. That's fine. And if you plug it in for this course, for the purposes of this course, this formula should be just fine. So now let's try to apply it to a specific problem. So here we have it. We've got a charged line like this, and we want to find the electric field at some point given a particular distance away. We'll tell you what the distance is in a second. So here's the idea, and here's some values, all right? So we're going to give you the charge, 3.3 times 10 to the minus 4th coulombs. That's the total amount of charge on this line. The distance that we're away is r, 5.6 meters away from that thing. And then L is 10 meters. So imagine we've got this charged wire or line. It's like 10 meters long. And now we just want to use our formula that we got earlier to calculate the electric field at that particular point. So let's do it. So we'll plug in some values. Here's the formula, right like that. So what we need is Q enclosed. This is the charge that's enclosed by our Gaussian cylinder. That's the surface that we picked that will always intersect the field lines in a 90-degree manner. So here's the charge, Q. This is 2 pi down here. This is R, the distance away from the cylinder, or from the charged line, rather, 5.6 meters. This is the length of the line that we're looking at, 10 meters. And here's epsilon naught, 8.85 times 10 to the minus 12 farads per meter. And when we plug all these values in, we get this value here. 1.06 times 10 to the 5th newtons per coulomb. That's the electric field strength at that particular distance. And notice you can do it for any given distance r. I could give you a different type of distance, and you'd be able to calculate what that is. Now notice that this falls off as 1 over r. So the electric field around a charged line falls off as 1 over r. But you might remember that the electric field around a point charge falls off as 1 over r squared. So they're going to fall off in a different manner. So that is an interesting thing. And what about the electric field between two charged plates? Does that change with distance? No, it doesn't change at all. So you should be able to answer some sort of qualitative question about where does the electric field fall off fastest with distance? Around a charged point, around a charged line, or between two charged plates. Questions like that, hopefully you should understand as well. I'm not saying I'm going to ask them on the exam, but I might. And I just want to let you know how to answer them if I do. Hopefully this has been helpful to you. All right, good luck.